spill occurs, there are four main approaches: natural cleanup, containment and recovery, chemical dispersion, and shoreline cleanup. In many cases, a combination of all four will be required. This program deals with the use of dispersants. 140 knots, altitude 10 meters, and a handling skill that places 500 liters of dispersant precisely over an area of 50,000 square meters of oil. The application of dispersants from the air, shore or sea, if carefully controlled in the correct conditions and situations, can be an effective way of protecting the environment, especially when containment and recovery is impractical. As with all remedial measures, the use of dispersants has its limitations and has to be subject to continuous monitoring and control. Here, there is insufficient wave action for good mixing of the treated oil. Here, it is far too late. The oil has been allowed to weather and is resistant to dispersant treatment. And here, the aircraft altitude is too high and the dispersant is blown off target. Applied incorrectly, all too often in the past, dispersants can do more harm than good. They're also expensive, so high costs can be incurred to little or no benefit. An understanding of the potential toxicity to marine life, of the materials used, their properties, effectiveness, and methods of application are therefore of the greatest importance. When oil is on the surface of the sea in one concentrated area, it poses the maximum threat to coastlines and seabirds. The action of waves on slicks can promote the natural dispersion of oil into droplets. As these droplets become mixed through the water column, the oil is diluted to become more readily available for eventual degradation by microorganisms. In order to accelerate this natural process, it's sometimes appropriate to use a chemical dispersant. This breaks up the oil into smaller droplets, seen here as a milky coffee-colored plume, so that dilution into the sea occurs more rapidly. This process, if started early enough in the life of an oil slick, can remove oil from the sea surface and so prevent the formation of persistent water-in-oil emulsions and weathered residues, which are difficult to clean up. Dispersants contain a surfactant, or a surface active agent. This substance has a molecular structure that has part affinity for water and part affinity for oil. When evenly applied and mixed into floating oil, the surfactant becomes arranged at the oil-water interface. This reduces the interfacial tension between the oil and the water, and, aided by agitation, the oil disperses into fine droplets.
Contrary to popular belief, dispersants do not sink oil to the seabed, but disperse it as fine droplets into the top few meters of the sea. These fine droplets have a slow rise velocity. This means they remain suspended in the water rather than surfacing quickly. This demonstration shows the relative speed of small drops and large drops of oil rising through the water column. The rise velocity will also depend on the type of oil. For most black oils, fine droplets of about 0.2 millimeter in diameter are unlikely to return to the surface of the sea once dispersed. As well as promoting droplet formation, dispersants prevent coalescence of oil once the droplets are formed. Droplets which collide have little chance to regroup, as the surfactant agent remains for some time at the water-oil interface around them.
Extensive testing has determined the effectiveness of different dispersants on different oils. For the dispersant to work, it needs to be distributed throughout the oil. Most dispersants, therefore, contain a solvent carrier, which allows the surfactant component to penetrate the oil. However, dispersants are not effective on all types of oil. Experiments have shown that viscous oils over about 2,000 centistokes, or those which have pour points above ambient temperatures, are resistant to dispersants. Thus, it's inappropriate to use dispersants on many heavy crude oils and heavy fuel oils. Even those oils initially dispersible become viscous and therefore resistant due to the combined effects of evaporation and formation of water-in-oil emulsions. This means that response teams who decide to apply dispersant must act quickly. The time taken for these weathering effects to render a particular oil resistant depends on many things, for example, ambient temperatures and sea states. But in most cases, except in tropical conditions, it's unlikely to be more than a day or two. This does not necessarily mean that oil that reaches the shoreline after such a period is not amenable to dispersant. As on the shoreline, it's possible for the surfactant to penetrate even viscous oils with adequate dosing and long enough contact time. Often, it will be appropriate to conduct a small-scale field trial before embarking on a full spraying operation, either at sea or on the shore. There are a proliferation of makes of dispersant available, but most fall within two main categories: hydrocarbon solvent-based and concentrates. The hydrocarbon-based dispersants consist of a hydrocarbon solvent containing between 15 and 25% surfactant and have to be applied neat in a ratio of between 1:1 and 1:3 with the oil. They should never be diluted with seawater prior to spraying. Early hydrocarbon formulations, sometimes referred to as first generation, used toxic aromatic solvents, whereas present-day products, known as second generation, have an aromatic-free solvent. The concentrates, or third-generation dispersants, usually contain a higher concentration of surfactant. For optimum performance, it's preferable to apply these materials in a ratio of between 1:5 and 1:30 neat concentrate to oil. However, they can be diluted with seawater prior to application from vessels. The concentrates have largely superseded the hydrocarbon-based products for dispersion at sea because they require less agitation after application to oil, and their concentrated nature increases the time a craft can remain active before reloading. These characteristics also allow the possibility of using aircraft. Consideration must be given to the quantities of dispersant stockpiled and the logistics of manufacturing and transporting additional supplies in the event of a major spill. Potential storage problems must also be thought about. Compatibility with other dispersants, ingress of water, corrosive properties, and handling problems.
Although the toxicity of modern dispersants is far less than earlier first-generation formulations, their use is still not accepted everywhere. Different countries have different attitudes towards the use of dispersants. In some countries, dispersants must pass a series of tests before formal government approval is given for their use. Laboratory experiments have provided data on the toxicity of different compositions and strengths of dispersants on marine life, but there is little hard evidence from actual spills. Before an incident occurs, it is important to identify the areas potentially sensitive to dispersant and dispersed oil, such as fish spawning areas, shellfish beds, wetland areas, tidal flats, and lagoons.
It is frequently possible to make an assessment of potential effects, taking into account the ecological sensitivity of an area. This can be done from a rough estimate of the maximum likely concentrations of oil and dispersants based on dosage, water depths, currents, and typical sea states. The decisions where and when to use dispersant are never easy and seldom clear-cut. In some situations, the potential advantages of protection of coastal amenities and wildlife from oil are greater than the disadvantages of the potential effects of the dispersant. But the use of dispersants may be rejected in other situations, even if the risk of damage is slight. As difficult as these decisions are, it is vital that priorities and a code of practice are drawn up before the occurrence of a spill.
This point here is not too bad.
In a time of emergency, such decisions will only be more difficult. In the event of a real spill, once the decision to use dispersant has been made, it is important to act quickly, as the properties of the oil will rapidly change, rendering the dispersant ineffective. application methods and rates will depend primarily upon the size and location of the spill, on the type of dispersant, and the availability of vessels or aircraft. Spraying from surface vessels is an established method, particularly for small spills close to shore. Specialized equipment should be used, rather than fire hoses and monitors, to avoid excessive use of dispersant. Spraying vessels vary considerably, from large ships with purpose-built arms to converted local fishing boats. The smaller vessels do not have the storage room needed for large quantities of dispersant and are unsuitable for large spills. Assembling spray booms and pumps on vessels is not easy and takes time. Rehearsal of these operations is essential. The towing of surface agitation boards mixes the dispersant in with the oil and can increase the effectiveness. Vessel design often makes it necessary to mount the spray arms aft. On some vessels, this can result in reduced treatment rate, where the oil is pushed outwards by the bowway. More effective results have been obtained by spraying undiluted concentrates from long fixed arms over the bow of the vessel. The concentrate dispersants need less agitation. This avoids the difficulties of handling breaker boards, the bow wave problem, and enables a greater speed and width of spraying. Whatever method of spraying, the application rate of dispersant should be matched to the thickness of the oil. This can be achieved by controlling the pumping rate or by varying the speed of the vessel. The correct pump discharge rate can be calculated from the chosen application rate, the speed and spray width. If such calculations are disregarded, the dispersant will either prove ineffective or will be wasted. Even when discharge rates are carefully monitored, vessel spraying techniques will always have certain limitations. The treatment rate is inherently low, and it's difficult from a vessel to locate those concentrations of oil posing the most significant threat. The formation of oil into windrows also makes it difficult for vessels not to spray clean sea at times. It's important to treat the thickest regions of the slick and not to waste dispersant on sheen. Aircraft with good communications are essential to assist vessels to coordinate their operation efficiently and evaluate the effectiveness of dispersant treatment. Since aircraft are necessary in such an operation, it's worth thinking about using them to spray the dispersants themselves, although when larger planes are used, an additional spotter plane will be necessary. The development of effective concentrate dispersants has improved the potential for using aircraft. Aerial spraying can now give the highest treatment rate and most cost-effective use of dispersant. It also has the advantages of good vision and of rapid response. The type of aircraft chosen for dispersant spraying should ideally be determined by the size of the oil slick and its distance from the shore. Helicopters are particularly useful in certain situations where there is a need to operate from a base close to the spill. Small fixed-wing aircraft can be effective for small spills or fragmented slicks close to the shore. They often have low fuel consumption, rapid turnaround times, and can operate from short or even improvised runways. Larger multi-engined aircraft are usually required for the bigger spill. Their range, payload, speed, and safety are all capabilities that often overcome the greater operational support and longer turnaround time required. Local runways and availability of aircraft, as well as supplies of suitable fuel and dispersant, may restrict the choice considerably. This should be studied at the contingency planning stage.
Aircraft that are suitable for spraying will be able to fly at relatively low altitudes, at low speed, and have good maneuverability. These capabilities should be considered against a high payload. Helicopters with onboard or underslung spray systems, single-engine agricultural spraying planes, and converted multi-engined aircraft have all been used in an oil spill response role. Individual circumstances will often determine the type of aircraft selected. The distance of the spill from the shore may exclude certain aircraft because of their operational limitations over water. The size of the spill may be such that large multi-engined aircraft are needed to carry the payload in the time available. Whatever aircraft is chosen, safety regulations, maintenance, runways, fuel, and dispersant availability should be considered carefully long before its deployment.
Spraying systems fixed to aircraft normally consist of a tank, a pump, and a spray boom with a rotary device or a pressure nozzle. Helicopters may be fitted with underslung bucket spray systems. More than one bucket reduces turnaround time. Whilst these have the advantage that the spray pattern is less affected by the downdraft, it is more difficult to maintain a safe low altitude. As with spraying from vessels, it is vital to calculate the required application rate for the thickness of oil to be sprayed, and to concentrate on areas where the oil is thickest. When doing this, allowances must be made for losses of dispersant spray in the air before it hits the sea surface. Calibration tests may help determine these losses for a particular aircraft spray system. Large dispersant droplet size and low altitude flying into the wind have been shown to increase the treatment rate. The application rate can be adjusted to the estimated thickness of oil by varying the speed of the aircraft and the dispersant flow rate.
Dispersant flow rate and drop size can be altered by adjusting or modifying the pressure nozzles or rotary devices attached to the spraying system. For agricultural spraying, equipment is designed to deliver low volumes of small droplets. It has been modified to increase the application rate and the drop size for dispersant use. This T-jet nozzle can have the swirl plate removed to widen the opening. And this rotary device has had the cage changed to produce large droplets. Rubber diaphragms can become perished by dispersants and other spray devices easily blocked. Because of this, frequent inspection and maintenance of all spray equipment is essential.
Aircraft, too, should be maintained and regularly checked, as dispersants may attack rubber components and contaminate lubricants. Because of this, it's advisable to hose down aircraft with fresh water after use. Strict safety controls concerning all aircraft operations, flight times, minimum altitude, and ground organization must be exercised meticulously, despite difficult working conditions in an emergency. Flying over the sea at low altitude can be extremely arduous. Despite exhaustive attempts by skilled aircrew, if the currents and winds are unfavorable, oil frequently reaches the shoreline. Where the wave action is strong, beaches may be self-cleaning and should be left alone unless there are overriding circumstances. Dispersants should only be applied to the shoreline when the pollution is light or during the final stages of cleanup. As at sea, these chemicals should be handled expertly in specific situations if they are to be effective without causing damage. Protective clothing is vital. When pollution is heavy, it's important to remove the bulk of stranded oil by other methods before spraying dispersant, as the chemical won't penetrate thick oil. This beach has already had much of the severe contamination removed by mechanical methods, but there is still a lot to be done. The workforce have decided to carry out small field tests before mounting a larger operation to discover the effectiveness of the dispersant at different application rates. The decision has been made. Several lighter treatments, followed by seawater washing within half an hour of each application. This process will minimize the penetration into the beach material. In general, oil should be sprayed with dispersant just ahead of the advancing tide, using the sea as a washing agent. When When dispersant use is accepted as part of the overall response, care should still be taken when assessing application rates and suitable locations. An assessment of the dilution potential is a useful basis for deciding when and where to spray dispersants. High concentrations may persist in shallow waters, and application here may have to be considered very carefully. Shellfish beds, inshore fishing areas, spawning areas, nature reserves, and others may be sensitive to dispersant. But of course they are all sensitive to oil, and difficult decisions will have to be made. In order to formulate a policy on the use of dispersants, the risk of environmental damage resulting from dispersant use must be balanced against the probable effects of the untreated oil. Advanced planning and the training and cooperation of interested parties will ease these decisions in times of emergency. For when used correctly and properly controlled, dispersants can be an effective weapon against the threat of spilled oil. Spill occurs, there are four main approaches: natural cleanup, containment and recovery, chemical dispersion, and shoreline cleanup. In many cases, a combination of all four will be required. This program deals with containment and recovery, an ingenious solution to a difficult problem. This rice straw and wire netting, although only a temporary answer, is providing one of the fundamental approaches to oil spill response: containment of the oil on the water surface for subsequent recovery. If oil is to be collected from the sea surface, some form of containment is necessary to prevent spreading. Once oil has spread and become viscous due to evaporation and mousse formation, the possibility of recovering it from the sea is reduced. Containment close to the source can not only localize a spill and reduce pollution, but it also facilitates the recovery of the oil by concentrating it in thicker layers on the surface. This can best be achieved by deflecting oil to a suitable collection point or containing the oil in a moored or towed boom. If a decision has been made to contain oil, A rapid response is essential. Equally important is the prompt removal